Hello, chemists! This is Miss Placino, and you are watching lesson 1.1 on properties and changes. In today's lesson, we're going to work on classifying chemical and physical properties and changes. We've got 3 goals for today's lesson. First up, you should be able to define chemical and physical properties and changes. If you've done the reading related to this lesson, there's a good chance you can do that already. Next, you should be able to classify changes as being either chemical or physical in nature, and a lot of the practice problems that we look at today are going to focus on that. And finally, you should be able to draw and interpret particle diagrams regarding physical and chemical changes. Don't panic if you don't know what a particle diagram is. Chances are by now you've actually seen them. Maybe you just didn't know what they were called. We'll review them before we start doing anything related to chemical and physical changes with particle diagrams. All right, let's get into the lesson. We'll start with physical properties and physical changes. Observing a physical property or undergoing a physical change will not alter the identity of the substance. And that's really the key, will not alter the identity. Observing a physical property is usually done just through your 5 senses. What color is the sample? What does it smell like? What is the texture? You probably wouldn't want to taste most samples in the chemistry lab for safety reasons, but when you observe a physical property, you don't have to do anything to the sample. Undergoing a physical change changes the way the particles or molecules are arranged relative to each other, but it doesn't change the chemical makeup of your sample. Let's talk about an example. We'll look at a popsicle. If you think about what makes up a popsicle, you've got sugar, water, and probably some artificial coloring and artificial flavoring. Right now, the popsicle is frozen, so it is a solid. I'm sure you know from experience, if you leave the popsicle out over time, it will eventually melt, and part or all of it will become a liquid. This is an example of a physical change. Nothing has happened to the structure of the water molecules or the sugar molecules or the artificial coloring and flavoring molecules. They're still the same chemical compounds. What has changed is the degree of organization. Instead of being in a rigid structure like a solid, now the particles, once they've melted, or the molecules, however you would like to think of them, have more freedom to move and are not nearly as organized. So that is a physical change. And it's worth pointing out that all phase changes are examples of physical changes. Let's review phase changes just to make sure we're all on the same page. You should have this in your notes. These are examples of particle diagrams. With a particle diagram, if you just imagine that you were shrunk down really, really small, so small that you could see the individual atoms that make up a substance, and then you drew what you saw, that is a particle diagram. And usually we'll represent either atoms or molecules just with these little circles. So 1, 2, 3. Those are representative of 3 phases of matter. You're probably familiar with them. Number 1 is, of course, a solid. 2 is a liquid. 3 is a gas. And we'll get up to that 4th one, that last one up at the top, in just a minute. All right, so to review phase changes, as we go from a solid to a liquid, we call that melting. Let's go in the opposite direction. When a liquid becomes a solid, we'll call that freezing. Next up, liquid to gas. Couple different terms you could use here. I've got evaporation. You might use boiling or vaporization. They're all discussing the same, or describing, I should say, the same phase change. When a gas becomes a liquid, that is called condensation. Hopefully you're pretty familiar with those 4 terms. These last 2, between the solid and the gas, a little bit more exotic. If we go from a solid directly to the gas phase, that is called sublimation. Something like dry ice, frozen carbon dioxide sublimes. The reason we call it dry ice is because it never makes a puddle. It's never wet. The solid frozen carbon dioxide becomes a gas directly. And we call that phase change sublimation. The opposite of sublimation, taking a gas and turning it into a solid, is called deposition. A good example of this would be, when it's really cold outside and the water vapor in the air ends up touching something that is also very cold, maybe a windshield or a blade of grass, and it immediately goes from the gas phase as water vapor into a solid ice. So like frost sometimes is formed through deposition. Those are the 6 phase changes and the 3 phases of matter I'd like you to be real familiar with. This last one up here is plasma. Plasma is an ionized gas, and actually going from gas to plasma is called ionization. Gas particles, or atoms of gas, or molecules of gas, however you'd like to think of them, are neutral. They have no charge. When a gas becomes plasma, those particles are ionized into positive and negative charges. Just like all the other phase changes, this one's reversible as well. The plasma ions basically can recombine, a process called recombination, and reform the gas. So those are a little bit more exotic. Really, again, focus on the 6 that occur between solids, liquids, and gases. From the bottom of this diagram up towards the top, you should see an increase in energy. So go ahead and see if you can answer these 2 questions. Which changes represent a loss of energy, and which of those phase changes represent a gain of energy? Pause the video, try them out. All right, so the phase changes that represent losses in energy. Freezing is an example. We go from a liquid that has more energy down to a solid with less energy. Same thing applies to condensation. And finally, deposition. All of those changes, over the course of the change, energy is lost. As you would probably deduce, the opposites in each of these cases represent a gain of energy. In order to melt a solid, you have to provide energy to the solid. Same thing with evaporation. Going from liquid to gas requires energy, and sublimation. The solid has to gain energy to become a gas to sublime. All right. Let's talk a little bit about chemical properties and changes. Observing a chemical property or undergoing a chemical change will alter the identity of a substance. If I want to observe a chemical property, I have to test it. For example, I might not know if something would react with acid or if something is flammable just by looking at it. I have to go through and subject that chemical to acid or try to light it on fire to test its reactivity or flammability. After that happens, the substance is fundamentally changed. Bonds have broken, new bonds have formed, and I've created a new substance. So, favorite example of most first-year chemists, lighting something on fire. That is always a chemical change. Whatever you started with, after you light it on fire, it's safe to say that you've produced compounds that are definitely different from the starting materials. Chemical reactions are examples of chemical changes. They're really 2 different ways of saying the same exact thing. All right, let's try some practice problems out. Okay, here we are in your practice problems, and I want to look at questions 1 through 5. And all you need to do is determine whether this is describing a physical or chemical change. So go ahead, pause the video, see if you can, based on what we talked about in the PowerPoint presentation, determine if those are chemical or physical changes, and we'll pick up in just a moment. All right, let's take a look. Melting copper. Hopefully you saw the word melting, and you remember that melting is a phase change, and all phase changes are physical in nature. Burning sugar. Burning is lighting something on fire. There's another kind of key word there. Anytime you light something on fire or run a combustion reaction, that's an example of a chemical change. Tarnishing. So silver, over time, is trying to develops this kind of grayish film, and it needs to be polished. That's actually a chemical reaction occurring. Silver is reacting with oxygen in the atmosphere. So this is an example of a chemical change. And I'd be aware of the word tarnishing or rusting or corroding. They're all kind of describing the same process of a metal reacting with oxygen in the atmosphere. Mothball sublime. Sublimation was one of the phase changes that we talked about, so this is definitely a physical change. And last but not least, HF reacts with glass. HF is hydrofluoric acid, and hopefully the word reacts is kind of a dead giveaway that this is going to be a chemical change. Remember, chemical reactions are just another way of saying chemical change. I'd say practice with the other problems. Make sure that you get comfortable with identifying changes as either being chemical or physical. Let's get back to the PowerPoint. I want to finish today's lesson talking about particle diagrams. And just to remind you, a particle diagram is a drawing of a substance on the molecular level. You've got these 4 molecules drawn in your workbook already. Hopefully you recognize these as water molecules. The red circle is representative of an oxygen atom, and those 2 little white circles, those are hydrogen atoms, and this is the geometry or the shape that they take on. Over the reaction arrow, we have this triangle. You might recognize it as like a delta sign from math class. In chemistry, that usually means heat. So I'm taking my sample of water molecules and I am heating them up. What I'd like you to do is pause the video and kind of sketch the change that you think would occur as water molecules are heated. All right, hopefully you've drawn maybe something like this, where you've taken those water molecules and you just spread them out. You haven't changed the water molecules at all. It's still 2 hydrogens bonded to an oxygen atom, but the arrangement of the particles is different. Does this represent a chemical or a physical change? Hopefully hopefully this looks like a physical change to you. Again, we still have water molecules on both sides of the reaction arrow. Just the arrangement, the organization is different. So this is definitely a physical change. Let's look at another one. This time we've got 6 water molecules as our reactants. And over the reaction arrow, we have this lightning bolt, which you might guess represents electricity. Do not try this at home. Don't try to pass electricity through water. That's not going to end well for you. Now, using your amazing powers of deductive logic, you can probably conclude that this is going to be a chemical change. What I'd like you to do is pause the video and try to draw what a chemical change might look like. All right, since this is like our first lesson, you're going to get a lot of leeway on what counts as a correct answer. But ideally, you drew something that looks like this. As long as you did not draw 6 water molecules just in a different arrangement over in the box on the right-hand side, the products box, your answer is going to be acceptable. This process is known as electrolysis, where we take electricity and we use it to break a compound back up into its elements so we can create oxygen gas, which would be those guys right there, the red ones, and hydrogen gas, the little diatomic molecules with the white circles. But as long as you do not draw water molecules on the products box, you're going to get credit for your answer. This is definitely a chemical change because the identity of the material has changed. We've created brand new substances. You definitely don't have to be a great chemistry student to know that the picture of the molecules on the left-hand box is very different from the right-hand box, and that's what makes it a chemical change. All right, that does it for today. Thank you for tuning in, and I hope you found this lesson helpful.